Yeah, thanks everyone for being here. Thanks to Laure for the invitation and also preceding me in the talk. I think her talk was a perfect introduction to mine, and a lot of similar aspects were covered. So we will be doing something very similar to full weather forecasting, but our forecasting target will be station observations instead of a full grid. And one motivation that I use to explain why I'm still interested in targeting the observations rather than the full grid is that for problems like power production forecasting. So if you put yourself in the shoes of a grid operator, you're facing increased pressure due to air data center buildups and other increased use in power production, and your production pattern, so where the power comes from, is also getting more and more complex and dependent on weather because of the increased dependence in renewables. There are still stakes, right? This year we saw a grid collapsed in the Iberian Peninsula, so in Spain and Portugal. So it's not a solved problem by any means, and we actually need to keep monitoring and improving the solutions that we have to manage these power production flows. One point I'd like to make is that to be successful in that task of power grid operation and power production forecasting, you need a good forecast, but they also need to be spatially localized, because if you have like these kinds of transmission lines, it's very important to you to know if there's going to be correlated effects in the wind production at all these sites, for instance, and then that would have a very large impact on the production on that line. This problem needs to be optimized continuously, right? So if you can spread your production better, then you're more efficient and you have less losses during transport. So you need to keep working at it, and there's always gains to be made. Okay, you're dependent on weather forecasting. You want to know what the weather is going to be at different sites. So the first approach you could have is to grab the nearest grid point from your local regional model that's produced by your national agency. So you do an initial interpolation, and you grab that value, say wind speed, and you use that value to input as an input to your power production models. But actually, if you were to do this, you're going to notice a problem. Pretty quickly, you'll realize that there's systematic statistical mismatches between what you observe at your production sites and what the AROM output gives you at a high resolution. And there's many explanations for this. An easy one that often pops up at first is that there could be a mismatch between your station elevation and the grid point elevation. So if there's 1,000 meters difference, you need to remove something like 6 degrees to your forecast to get the actual temperature that you're expecting to observe at your station. That's easily solved, but then there's other issues that are not as easily solved. There could be local unresolved effect, right? Your grid resolution just isn't sharp enough to pick up that the bay that we have here is affecting the temperature and the wind speed that we're experiencing, and that can create these mismatches, and that's not as easily resolved. Or you could be simply that your subgrid parameterization, I mean, it's a related effect, but your subgrid parameterization could have been optimized somewhere else. And then it's not as good for your particular case. And so this is a computer generated image that I used to explain local effects, but you could have updrafts caused by particular topography. You could have water that is not present on your grid, and then this affects temperature and wind locally, and something that can't be picked up by the larger resolution models. And this problem has been studied for a very long time. There's a subfield of meteorology called weather forecast post-processing that is concerned with the statistical calibration of weather forecast output. So this idea of grabbing the nearest grid point, looking at the overall weather state, and try and map that to what we're going to observe is actually a well-known one. And the overall strategy is really it's really a machine learning strategy. I mean, it would have been called like that at the time. I mean, it was more the field was more occupied by statisticians, but really it was machine learning, right? You supervised learning setup. You grab a bunch of features or training predictors from your forecast, and then feed that to a model and try and get out of that a predictive model that will get you closer to the observation that you have in your data set. And as Laure mentioned, ensemble forecasting is a very standard way to do weather forecasting to account for any uncertainty in the initialization, in the initial state, and also model rollout uncertainties. So if we were having an ensemble model, then we also wish to have an ensemble model post-processing where we are able to provide probabilistic assessments of the future sensor states at these ground stations. And if you go back to about the beginning of my PhD, maybe a little bit earlier, you'll find that weather forecast processing is a very alive field, and there's a ton of methods, and they all have specificities, right? So if you look at this review paper, they had this nice, easy to implement, hard to implement with a simple neural network here, which, I come from a computer science background. So that attracted my attention that the neural network, simple MLP would be considered harder to implement, but then you have also familiar methods. EMOS is a linear prediction with a distribution at the end. So if you expect your temperature to be normal, you can output a mu and sigma parameter using a linear model, and then have this normal distribution as your expectation of the temperature, for instance, at the station. And then they had this classification in two colors, right? So the blue methods would make a distributional assumption, so grab a classical distribution, so normal distribution, sensor normal distribution, gamma, and use that. And then the orange method are distributionless, that they call, but essentially it often means that you're predicting quantiles directly, so you could choose a resolution, say 50 quantiles, and then use the same types of models to predict all these values. And if we take a step back and look at this method as I said, at the beginning of my thesis, or just about, well, the methods are numerous, so there's no consensus on how this problem should be handled, and it often depends on the variable you're targeting. So it's really a last mile problem where we're trying to extract as much performance as possible that we can from the forecast. So because of that, the methods tend to specialize. And post-processing is mostly done independently in space and time, and this is the focus of this talk, is that there was this compromise where you had to kind of choose between calibration and physical consistency. So you could either have a scenario at all your stations that is physically realizable, or you could have one that is well calibrated, but it was kind of hard to get the two, and the methods that we had that we have to restore or preserve the correlation structures are lacking in power in regard to the new methods that we know now, and cover these a little bit later. And in all that context, you also have to contrast this with another figure that is kind of similar, and that was basically this is basically the first part of Laure's talk, right? We have AI-powered weather forecasting methods. So new modeling methodologies have emerged that are very promising in the field of weather, and which, this is for weather forecasting, and we're doing post-processing, which is a subfield, but it kind of puts things in perspective. Which brings us to a question, which is how do we address these known limitations of weather forecast post-processing, namely the lack of spatial consistency and temporal, although I won't be covering much of the temporal aspect today, but so another way to frame it is that we have an opportunity to kind of try and reimagine station-wise forecasting given the new methods that have emerged. And I wanted to spend a bit of time about generative modeling, but that was covered by Laure and Sibo, so I'll just go through the motions anyway because I have the slides, but the early data-driven weather forecasting models, so the first ones that achieved better RMSE than an IFS ensemble mean, so that kind of beat the gold standard, were trained in a deterministic fashion, and there was this series of models. So they would target the RMSE, and they came with a family of which I call this early model limitations. And these models were initially criticized for a familiar set of defects that you see often. And what we have seen, I will argue, often in this workshop this week. So a lot of forecasts will have will be smooth and blurry. They underestimate extremes, and then they miss intensity peaks. And these criticisms are kind of crystallized in this paper here. And yeah, so you know, we can keep criticizing them, but actually, I would argue that we could have expected these defects from theory. Because when you when you have this very, very classical supervised learning setup in machine learning, where you have this model, you have predictive features, and then you fit the RMSE, so you optimize the RMSE given your feature, and you try to make a prediction. Then what you are targeting is the conditional expectation. And I have, so this is, for me, the best way to explain this. It's an extract from the GenCast paper, so a diffusion approach to weather forecasting developed by Google. It's their second iteration on weather forecasting. The first iteration was GraphCast, and GraphCast is a deterministic model. It's trained using the RMSE. GenCast is a generative model, so it's trained using another paradigm. And the big difference between a supervised learning setup like GraphCast and GenCast is that instead of targeting and trying to predict the conditional expectation, we're trying to target actual samples from the distribution of plausible realizations of the atmosphere at that time. So we have for warm field, so this is atmospheric pressure at 700 hectopascal, pressure. and you know, you have some resolution here, and then in the GenCast sample, which uses a generative model, you have more resolution. And then if you look at the ensemble mean and compare that to GraphCast, you realize that GraphCast is actually much closer to your ensemble mean than an actual realization, a physically plausible realization from your forecast. So this is a point I want to kind of wanted to hammer in because the blurry forecast and underestimated extremes criticism comes often, but actually it's for me it's more of a misunderstanding or misinterpretation of what your model output is. Okay, and I stated in my objectives, I stated that I did want spatial consistency and I wanted good resolution. So because of that, I need to reach for generative modeling tools for my approach. And so I developed, as part of my thesis, something called FMAP, which is flow matching post-processing. So yeah, and I started using, I'll talk about that later. It's a generative model, it's based on flow matching, and if you haven't heard of flow matching before, just substitute these words for diffusion, and everything will be fine. It's the same as diffusion. You know, the theoretical frameworks used to arrive at the models are different, but then the consequences are the same. They're exactly you use them the same way. And the principle has already been explained this week, is to, instead of trying to predict your conditional expectation using the RMSE directly, you're going to train your model to perform distribution transport. So you start from a distribution that we know well, which is a normal distribution. And then what you learn is a model that transports the distribution towards your distribution of interest, which is more complicated and that we could not sample before, right? So QZ, which in my case, it would be you know, a vector of 120 sensor measurements over all of France, for instance. Right, that's going to be our target. And the model we learned, it has to be called iteratively to perform this distribution transport from the normal distribution towards the distribution of interest. And we often talk, you know, we often say that the choice of loss will affect the shape of your results and the functional that you get, but it's a little bit imprecise because the loss that is used for flow matching is actually the RMSE. You're learning so this is the delta between your standard normal sample and the sample that you're trying to target, so that vector that we're trying to have, and then this is your model here. And the loss is the RMSE, and it turns out that if you optimize for that RMSE and then you perform distribution transport, you do this process as we have been describing here. So it's not really the choice of loss, not exactly, it's the choice of, I don't know, like generative modeling framework, I would call it. And that will greatly affect the shape and the type of objects that you get. Are you getting an actual sample, or are you getting some form of functional over your distribution? Okay, so we want to use flow matching. We want to use it to do in situ weather forecasting or weather forecast post-processing, and then I get the opportunity to dive into a little bit more details. The overall architecture looks like this, but I split it in parts to make it easier to digest. So the overall process looks like this. We get a gridded NWP forecast. We extract the region of interest. And then we extract two things from it: the raw ensemble mean, which will, on which we will base our correction. So actually, what we're going to be targeting is deltas or residuals or corrections to apply to an ensemble mean to bring them from a statistical ensemble mean to an actual sample of a distribution. We have a transformer backbone, which is called iteratively to perform this distribution transport step, and then the initial sample, which I was talking about, which is a normal sample, is here. And obviously this is weather forecasting, so we need a condition, right? It's not we're not generating one plausible sensor state from among all the sensors that we condition an initial conditions, or here is here is the NWP forecast.
Sorry, the distribution you are talking about is the probability distribution in some large dimensional space corresponding to the point you are the sites you are targeting.
Yeah, so you will see in my first example, and I think the only one I covered today, we have a 240 long vector, which is not as large dimensional as a full, gridded weather forecast.
Okay.
I would call that intermediate dimensional space, the 240, and this allows me to do things that aren't exactly scalable to a full gridded forecast, but
it's a distribution in that space.
Yeah, and then we sample from it.
And the Gaussian model you start from, it's IID Gaussian.
Yes.
In that
Yes.
space.
Identity matrix for your covariance. Yes. Yeah. Yeah, and in the end, if we add our raw our ensemble mean to the residual that we learn, we get the post-processed in situ weather forecast. The backbone is a transformer, and I have a little bit more about this, so I won't delve into the attention mechanism because I have a better figure for this. But what's important to tell is that you have an input sequence. So transformers operate on sequences, and as a user or a downstream application, you will not be concerned with the transformer architecture. It's kind of standardized by now. It's been around for a few years. So most of your work will be in designing the input sequence so that it fits well into a transformer and that you can get the results you want. So here in the input sequence, I will put my conditions that are stemming from the NWP forecast that I'm post-processing, and then the state that we sample, so the state that we're manipulating and transporting, and also the flow matching time, which goes from 0 to 1, 0 being a normal sample and 1 being the sample from the distribution of plausible weather states. And then this is called 16 times to get the residual I was talking about. And then if we zoom on the input sequence, you see that so every column here on that big matrix is represent one station, so one spatial location. And then we have a concatenation of the nearest column extracted from the NWP forecast, the state, flow matching time. This is mapped to an embedding, and this bit here is quite important. So it's a station embedding. So it's a learn. So at first, when I start my model, this is just a random bunch of numbers that I've initialized. But then I add this to the tokens. And the reason we have to do this is that transformers are not aware of the spatial location. I provide features like latitude, longitude, and elevation. So that's already in there. But transformers are not aware of the kind of the semantic relationship between the stations. And I know there is one, and I'll show you on the map, but basically some stations are closer to each other than others, right? So these two stations should be related. If we're going to build something physically consistent, the transformer should be able to learn to build relationships between stations. And the main tool, it has to do that, and also the main tool, it has to take notes or encode the local microclimate or the local effects around the station, so the kind of take notes about what the function is from the NWP forecast to the observation will be stored in there. But it's also an important bit because this is where we break invariance assumptions, right? So the presence of that embedding means that our model cannot really trivially be extended to new spatial locations. We need to have a place with measurements, which is the scope I gave myself, right? But Another way to frame this problem would have been to be able to spatialize, like Jonathan did. But we're not trying to achieve that here, and because of that, we can get away with a station embedding there. Okay, how do transformers work? I talked about building relationships between stations, and also there's competing paradigms. This conversation between graph neural nets and transformers. And what's funny is that the first model of Google, GraphCast, heavily emphasized the graph neural network nature of the model. And then for GenCast, which was their second iteration, the diffusion model, they described the exact same model as a transformer, as a sparse transformer. So they use the same words interchangeably to describe approximately the same thing. And those of you who have more of a computer science background will recognize the adjacency matrix formulation of a graph. But basically, you can alternate between the two because your graph is here, your transformer attention matrix is here. But what happens is that you build relationships between stations, right? So imagine each of these points is a station, then you can have a heavy connection by having a higher value in your attention matrix. And then you can have no attention by having a lower value in your attention matrix. So the way transformers work is that first it will look at all your stations, the data you have, or the representation, the abstract representation you have at all your stations, and find a way to see what the mappings are. So where should I send, how should the information circulate in that graph? And then the equivalent way to pose this in a graph neural network would be to build a fully connected graph, so every station is connected to every other station, and then let the graph neural net figure out how to circulate information within this to create physically consistent scenarios. And I personally chose transformers because I didn't want to mess with this. My state is very small, it's 126 long, right? So I can live with the fully connected graph and then let the model figure it out, which maybe is not something we can afford with larger models. Yeah, so station embedding, I've already covered this, and then also I will underline that since I already have an ensemble forecast that has been generated, I can start from the ensemble mean. And in weather forecasting, you're not so lucky because you don't have the weather forecast. So some models have two parts, like they have a deterministic model that gives you the conditional expectation, that blurry thing we were talking about, and then they learn the residual from this. And this tends to help the flow matching process. It makes it easier to resolve, right? Because this flow matching process is a numerical integration like we have for the ODEs for weather forecasting, like Navier-Stokes and stuff. So you have to, if you can design it in a way that is easier to resolve, it's a good thing. It means you're going to need less integration steps during the generation. So it's been popular to, or at least some people have been generating first a deterministic model and then a diffusion or generative model on top of it to make the diffusion easier. But here we didn't need to do that because we already had an ensemble mean which approximates the deterministic model quite well. Okay. So I showed you the architecture. We're going to take this on the EUPP bench dataset, which is a dataset that was developed by the post-processing community for this kind of applications. It contains reforecasts for over 20 years, so I think about 4,000 reforecasts. And then I also have a corresponding sets of forecasts that have been done on very similar model versions. So we don't account for model updates or model modifications in this. And for here we have about 121 stations, and we're going to be predicting two variables, so temperature and wind. And we start from a 0.25 degrees model. So this is what it looks like. Probably should have showed this earlier. A good illustration of what we're trying to achieve. So we're trying to achieve temperature and wind speed at these locations given a gridded forecast over the corresponding area. Another important implementation detail is that we're getting a, sorry, I keep confusing the buttons. We have an ensemble here and we have to find a way to input this to the model. It's quite heavy to input all of the individual members inside the model. So actually one of the first things that we do is that we smash this into a mean and standard deviation, which you could criticize, but it looks like it didn't affect us too much, and I show that in the results. Because otherwise your input is overly large and it gets you a lot of trainable weights. Training schedule. Yeah, and another important thing is that we are in a time-independent context, and this is maybe an important characteristic of that model. So our underlying NWP forecast was every 6 hours for 5 days, and we use one model to do post-processing at all of these time steps, but we do not do all the time steps in a consistent manner. So we kind of start from scratch at every time step, which means that the time series we're going to be generating, let's say we do 50 members at 6 hours, then the 50 members we have at 12 hours are not going to be consistent. So that's an important characteristic of that method, and it's maybe the main limitation. And we can go back to that slide I had about post-processing and compare to baseline methods. So I don't want to bore you with like a ton of different models, but essentially here you have the idea where you try and predict a normal distribution to represent your temperature. So you have an MLP, a small neural network, that will be predicting distribution parameters from a classical distribution, and then we evaluate this against appropriate metrics. So this represents the blue points, right, the distributional methods, and then the non-distributional methods are represented by a quanti-regression network, which is essentially the same idea. It's just instead of predicting 2 parameters from a Gaussian distribution, you predict 50 parameters from a quantile, an empirical quantile distributions. And these methods are spatially independent, but our stated goal was to preserve spatial consistency. So we apply on top of these something called ensemble copular coupling, which is a method that looks at the correlation structures in the ensemble in terms of ranks. So it says, okay, if for this station my 25th highest temperature was paired with the 12th highest temperature of this other neighboring station, it tries to recreate these rank correlation structures inside the forecast. And then there's also this method, which is an energy score generative model, and that maps to the energy score, I'm not sure how Laure called these, the generative, metric-based generative models, essentially. So the generative models that are trained using a proper scoring rule. And I will be doing evaluation again in using metrics that preserve the correlation structures, because this was my stated goal. So the energy score is the multivariate extension of the continuous rank probability score. So it's a metric that, so if we start from the CRPS, it's a proper scoring rule. So that's an important property, and I couldn't demonstrate that property myself, but essentially what it means is that your model is going to be rewarded both for being close to your observation, but also for having a fair assessment of its dispersion. And so you have this being close to the observation term, being appropriately dispersed term. You can see you can improve your CRPS by increasing dispersion, but if you think about it, you notice that if this dispersion is very large, then necessarily some of your members are going to be very far from your observation. So that's how kind of things even out. And then the CRPS that's more well known, but that works marginally, so for one variable, one location at a time. But you can also do it in a manner that captures misspecification of the correlation structures, the spatial correlation structures, and that's what the energy score does, but the shape is the same. Okay, so the first result, I'm just going to show you how the flow matching works, because I think it's illustrative, but essentially you start with Gaussian noise, which has no structure, and then you call your model progressively, and you end up with something that's very structured. So that looks like a temperature field or a plausible observation of temperature at all these stations. So that's reassuring. It looks like we're working, and then if you do this sampling procedure for all of our forecasts for our test period, we can end up with plots that look like these. So I'll take a bit of time because there's a lot of information here, but if we start in the middle, we have temperature, wind. We have an energy skill score, so our score here is relative to another model, right? So we started with a basic distributional regression model with ensemble copular coupling, and then we compute essentially the percentage improvement over this. So there's 4 lines. Our method is the purple one, so this one here. And then this is the energy score generative model, which I don't have that much time to talk about. And then these are the more classical methods, right? So quanti-regression network is here, and we use the distribution regression network as a baseline. So you can see that our method in terms of the energy skill score brings large improvements. For temperature, it's almost over all the lead times, and then for wind gusts, we see better improvements over very short lead times. Then for multivariate, the idea is just to take the two vectors, so 120 temperature, 120 wind, and then compute the same thing, and the hope was that we would capture correlations between wind and temperature at the stations. The variogram score is similar, it's just that it does not account for biases. So you could be very far from the observations, but if your correlation structures are the same, then you have a good variogram score. So this one really hones in on the spatial correlation structure. So this is what we cared about, and we see that we have pretty nice improvements there as well. And then we can do some inspections. And this is one figure that makes me very happy, and it's also similar to the one I showed at the very beginning, right? The GenCast one. So you can see that we have the FMAP ensemble mean, which is not too far from what was observed. And then you can see that the individual members will have achieved spatial consistency, despite the fact that we started with a noisy, normal distribution. And what's very interesting to me also is that the mesoscale configuration varies, despite the fact that we fed essentially something that looked like this. So it's able to imagine spatial, consistent spatial displacements of the weather stuff. This is as much as I know, but the systems, I guess. So we can achieve spatial consistency here, which is encouraging. And if you compare this to the main competing method, you see that the energy score method had trouble achieving. So the small scale patterns are correct, but the large scale patterns are less. Though I will invite you to reserve judgment, because I don't think it's because of the generative modeling methodology here. I think it's more related to the model architecture that was chosen here. That is quite a bit smaller than FMAP, which was a transformer with millions of parameters. Metrics-based generative modeling using things like CRPS or energy score actually works, and I'm actually working on this right now. It's just this one did not do as well because its architecture was small. And so the power ratio was looking at the power spectra was not as easy for this problem because we need to spatialize it first, right? We have points on the map, so we needed to put these points on a grid and then compute the power spectra like people have been doing for GenCast or GraphCast. And we can see that our spectra are actually quite fine as a ratio of the against the observed spectra, right? So you want to be close to 1. And then ESGM, so the misrepresentation of large-scale structures that I was talking about is visible here, with the longer wavelengths being less powerful. And then the spread error ratio is interesting because we see that we have a slight under-dispersion for FMAP, so for the flow matching diffusion model. This is something that I was able later to improve with switching from a Euler solver at 16 steps to a second-order solver. But there's still slight deficiencies in the dispersion. And then I have marginal metrics. So if you take the forecast individually at every station, you see that you still improve things. And also the Breyer's curve gives us an idea of what happens at the extremes. So if you try to classify, am I going to be above the 95th percentile of temperature, for instance, we still do better than competing methods. So the scores are good overall, and we improved the representation of spatial structures, which was our stated goal. I'm not sure how I'm doing on time. Am I about done, or?
No, it's supposed to be 30 minutes, so we are there, right? But we are not so. We have some time
because we're going to coffee break. Okay.
Today, so.
So about there. And my take-home message would be this, if I had to give one, is that, and I noticed this like in the last few months, but if you notice in this talk, I was referring to weather forecasting models as a comparison, and I spent less time on post-processing methods. So I started my PhD, I feel, with two distinct problems, but they are becoming very similar, and in future work, I would like to extend this to space-time consistent forecasting. So this is what I'm working on right now. So instead of doing it spatially independently, I'd like to be able to generate a consistent time series. And it turns out that the best solution I found for this was an autoregressive model, which is exactly the same as they've been doing in weather forecasting. So like this month, I kind of realized that, oh no, I'm doing weather forecasting on a very bad grid of 120 points. Which is interesting, but it's also remarkable that it's kind of this convergence of modeling methodologies, which means that we can share tricks between weather forecasting and post-processing. Now this is possible. And also the logical conclusion to this is that we should consider hybrid methods, so integrate observations into the grid and do it this way, which is exactly what Laure suggested we do as well. So I kind of reached the same conclusion, is that if I'm going to do full weather forecasting on 120 points grid, might as well do full weather forecasting and add the points I care about, which were the Institut measurements, and attach them to this grid. I think it's the way to move this forward. So I talked about generative modeling, I talked about FMAP, and the take-home message there. So I'll be happy to take questions now.